Hello again. Welcome back to this course on fundamentals of data science. Today we are going to deal with more information on Markov process. You have already learned about what is a Markov process and how things works out with probability transition matrix and how we can actually predict the future states. We are going to look at more information or more properties of this Markov process with respect to power of probability matrices and stochastic matrix, when we can call a matrix as stochastic, and finally we are going to see more examples on this Markov chain. So here is going to be the contents of today's discussion: understanding the steady state probability or steady state probability with stable matrix. In other words, how do we know that we reached a steady state or stability? In other words, we call this term as the stable matrix. When do we know that we have reached that equilibrium? And we are going to look at Markov chain based predictions in real time. So those are the two basic objectives for today's lecture. Let's start from where we have left in the previous lectures. So here we are going to discuss about this market penetration. So this time we have 4 states, or in other words you could say 4 stores, or in other words you can consider this as like 4 different products: product A, B, C and X. Say for example product ABC is already in the market and you are introducing the new product, that is product X. Say they are all of same things, maybe the use of soap or maybe any other product you can think about. So there is already ABC is 3 different, say soap or perfume we can consider. ABC is already there in the market and now you are introducing a new perfume X, and initially A has 40% of its market share, B has 32% of its market share, C has 18% of its market share. And one more thing is A retains 92% of its customers, C retains 90% of its customers, X retains 97% of its customers, and finally B retains 94 of its customers. And there is other things. The customer who are using brand B will be going to brand A. You could say 3% of them go to brand A, 2% from brand A comes to brand B, and again 2 more percent goes to brand X. And for those person who are using brand X, 1% goes to brand B and 1% goes to brand C. Again for C, percentage who are using brand C, 6% comes to the new brand X and 2% goes to brand A and 2% goes to brand B. C also receives 1% from brand B and again 1% from brand A, and we know that 1 from the new brand X. Likewise, A, customers in A, 2% goes to brand B, 1% goes to brand C, and you can see 5% goes to the new brand X. And it also gets 1% from X, 3% from B, and 2% from C. So this is the overall probability transition matrix with all different possibilities. You can imagine we discussed about very simple probability based matrix, transition matrix, but now this matrix is a bit complicated, but it has a significant effect on it. Okay, let's put this in the matrix form. Here is the matrix actually, probability based matrix. As you can see here, from A to A is 92%, from B to B is 94%, they retains, C to C 90%, and finally X to X is 97%. So likewise you are evenly distributing this whole probability matrix based on the data given to us. An initial distribution, initial X naught is 40% for A, 32% for B, 18% for C, and 10% for X. Okay, so this is what we have. And as we know that when we multiply P times X naught, we get X1, the next state. Or if you want to know what happens to the trend of customers moving from one state to another state. In other words, after 1 month, what would be the number of percentage in A, B, C, D, A, B, C, X. And maybe after 2 months, you can consider, we discussed about these parts, if you recall. And after 3 months, after 4 months, so on and so forth, you can calculate. But after a certain period of time, it reaches the stability. In other words, it reaches the equilibrium part, after which it doesn't rise. So we reach a stable state or stable matrix. You can also call stable state, after which there is not much change happens. In other words, it stays at a certain level. So here the X bar, which represents the stable state or stable matrix, has been referred here to be like, this is for A, B, C, and D. So after several months or several years of these products, you can consider the domain like X1, is it referring month or year? Based on the data that we have, you can consider it as to be a month or a week or a year. So anyway, we are talking about next year, next month, or next week. Next is going to be X2, next, X3, and so on. So after anyway series of future states, it reaches a stability in which you can see there is a significant change that has been happening here. And eventually we get for, in fact this is not D, it is X here, and the X is a new product, and initially it was only only 10% if you notice, but now it has reached over 50% of the market is with the new brand X. But other things, like if you look at other brands, of course they have reduced significantly. For example, product C is reduced almost 50%. It has reduced from 0.18 to 0.091, and that has to do a lot with two factors if you notice. One thing is the customers retained by X is 97% customers been retained by X, and other one is the number of customers moving in to X. For example, from C 6% were moving in, from A 5% were moving in, and from B, well, 2%, but percentage of moving out is only 1% here, 1% here, 1%. Only 3% were moving out from X, but if you calculate the values from other brands moving in is more than who are moving out. So that contributes a lot to why this huge change has happened. But as I told you before, after a certain period of time it doesn't increase. So here is the market share. In fact, you could call it as market share. And after like several weeks, in this we will consider it as weeks. So probably like after say 15 weeks, it has almost reached its peak. Around 20 week, it has got the stability there. It reaches the equilibrium, and after which there is no more change. It remains the same for the future. Well, this is one way in which we can predict what has happened, and what is going to happen with the given data. With the current state, you can actually predict the future states. So that's one of the advantage of this form of Markov process. Well, let's deal more with the power of a probability matrix. Suppose the probability matrix P is given to us. In this case, the P that we have here is this 0.8, 0.2, 0.1, 0.9 is the P, and you can take the power of P times P. So P times P again, as you can see here, it reaches to this value, and then again you can think about P times P times P. In other words, P power 2 times P is giving you the new values for P power 3. So you can keep on calculating these values. So when you keep on calculating these values, you will arrive at, again, there will be a time when you reach the stability. In fact, here the P3, let me see here. Okay, I should have write P3, P power 3 should be 0.8, 0.2, 0.1, 0.9 times 0.66, 0.37, 0.17, 0.38. So when you multiply these two things, in fact, you will get this one. So this one you can ignore it. Maybe there is a typo mistakes. So this one we will get, and then for P4 we are again using this, multiplying these two elements, and you are getting this one, and for P5 again you are multiplying these two elements and you are getting this one. So this is how we get the power of the probability matrix that you have in hand, and you keep on doing this until you reach, again, there is a stability. We talked about initial condition with x0, x1, x2, x3, still we reach a stability of x bar. If you remember, in the past examples also we have seen this, until we reached this x bar. But now we are going in a different direction, in which we are going to look at the power of the probability matrix, and again power of the probability matrix also reaches its stability. In this case, P bar or P power n, at one point of time P power n, it reaches the stability. The previous value and the current value is same. For example, P power n minus 1 is equal to P power n is equal to P power n plus 1. They all looks the same. They are the same values. It reaches the equilibrium or stability, after which it doesn't increase. So in this case, this is the stable probability matrix. So with this stable probability matrix, we can actually have a stable distribution matrix. So what is that? So when you have this stable probability matrix, that is P power bar, and when you multiply this with your initial conditions, that is x0, you will always arrive at the part of stable distribution matrix X bar. In the past we did it in different way, but now you can also do it in this way. So let's try with different initial conditions. For example, let's try with initial conditions 1, 2 and 3 and see what happens. So in this case our p power n is p power bar is given to be this one, and the initial conditions, there are 3 initial conditions. We can try one by one to see what happens to the stable distribution matrix. Okay, here it is when okay, I think okay, here it is x naught equals 1 and 0 and x naught equals 0.5 and 0.5 and x naught equals 0 and 1. So this has to be 0.5 here and 0.5, this is 0 and 1. So when you multiply this values, you will end up with this 1 by 3 and 2 by 3, 1 by 3 and 2 by 3, 1 by 2 and 1 by 3 by 2 by 3. So they are the same, they remains the same. So this eventually is our final task. So this one we know, right? This one is p bar and here is the x naught, p bar x naught, p bar x naught. So x naught, the initial conditions are different. We are giving different initial values, but eventually you are getting up with the stable value there, x naught. So that is the property here that we have for the Markov based probability transition matrix. It reaches the stability. We can look at in different perspective. Okay, with this thought in mind, let's talk about what is a stochastic matrix. Well, stochastic matrix, it's quite easy for us to understand what is a stochastic matrix. One of the simple ways to understand what is a stochastic matrix is that when you add up the columns, it should always give us 1. For example, in this case, if you add up, it gives you 1, and it adds up, it gives you 1. So in this process here, the column wise, it adds to be 1. So likewise, you can also consider in a different perspective. So here this one is not stochastic, as you can see when you add up it's not equal to 1. So that's one of the reason why we call a matrix as stochastic and a matrix is not stochastic based on the distribution, how they are put up in this probability matrix. So here is one more information about the regular matrix. If P is regular, there will be P power n, where P power n times x naught is x bar. We discussed about this, where x bar is the stable distribution matrix. And we know that there will be a time when it reaches P power n plus 1 equals P power n. So that is, this P bar is a stable matrix. So we know that when you have the powers of P, like P times P, this is P times P, P power 2 is P times P, and then again you are multiplying and getting P power 3, P power 4, P power 5, and so on and so forth. So when you reach these values at a certain state, you will come up with the stable matrix of P bar. Okay, with respect to this Markov chain, we are going to look at a couple of examples here. So the first one is the charity contribution. Of those who have contributed for the charity, 40% will not contribute next time. So for those who have contributed, 40% will not contribute next time, and for those who don't contribute, 10% will contribute next time. So for those person who don't contribute, 10% will contribute next time. We call N as not contribute, C as contribute. So those who have not contributed in the past will contribute. This is, let's say, present state, and next state. So those who have not contributed now, they will contribute in the future. So based on that, you are filling the remaining ones like 0.9 and 0.6 to make it as this regular matrix with stochastic properties, and then you are going to find the distributions among the whole process, how it's happening. We are asked to find the final distribution matrix, what will be the stable state and how many contribute and how many don't contribute. We want to understand what is this x bar in this whole process. Okay, so with respect to this, we know that this condition exists. P times x bar is x bar, and with that we are going to consider this process with NC. NC is the N is not contributing, C is contributing. So we know that P times this is P, and we are having this as x bar and is x bar. So with that, we are trying to solve these two equations here. Based on that, like 0.9 times N plus 0.4 times C equals N, 0.1 times N plus 0.6 times C equals C. So you have two equations and you are trying to solve these two equations. When you try to solve the two equations, we come to know that there is some relationship coming up for N equal to 4C, and we also know N plus C is 1, right? The column should be equal to 1. So we are using this relationship and trying to figure out what is the value of C. For example, in this case, C comes to be 1 by 5, and once you found C, you are calculating N to be 4 by 5. So final distribution matrix x bar equals 4 by 5 by 1 by 5, which is 80% and 20%, which means that N, those not contributing, is 80% and those contributing becomes 20%. This is a simple example of Markov chain process. Likewise, even we didn't really go in deep to calculate the whole process with P times x naught, or we didn't talk about like P power N plus 1. We didn't talk about this P power N. We never had this in this example, but with the given information, still we applied the Markov chain process in this real world example and calculated the stable state matrix and found how many would contribute and how many will not. In the same way, we can also think about this problem here. I will just leave it up to you to look at this problem here. There are two stores, store A and store B, and this charity contribution problem and this grocery store problems are very similar. So you can check by yourself, all the steps are given to you here, and you can see how it is done, just like the way we have done in the past. Like we are going to look at the similar principle here. Based on that, you are going to solve for A and B, and finally you are calculating the stable distribution matrix. After finding this A and B, you will be able to solve it. Okay, let's look at more real world examples. So in this real world examples, the problem given to us in this case is that as you can see, the weather model in which we have the sunny day is 90% likely to be followed by another sunny day, So once you have sunny day, it will be followed by another sunny day 90%, and the rainy day is 50% likely to be followed by another rainy day. So if you are in a sunny day, you are going to be retained as in the sunny day for 90%. If you are in a rainy day, you will be retained the rainy day with 0.5% or 50%. So you can actually, based on that, you can form this probability transition matrix, and you can try to predict the weather for this whole process, how it is happening. So based on that, you can calculate, and this in this case of this predicting the weather, so weather on 0 day, for example today, is known to be sunny, and this represents by the vector sunny, we have entered like 100% if it is sunny, and rainy is 0%. So we have 1 and 0. 1 represents like 100% and 0 represents just 0%. So x naught is 1 and 0, and if you notice, we have shifted our whole process into this a different format. Initially, in previous example, we talked with the column format. Now we are talking about row format. So that's why here x naught is a vector with 1 and 0. We have shifted this in this form, so that you also have the p here have been shifted in the row form as well, like 0.9, 0.5, 0.1, 0.5. That's why when you add up this one, it comes to be 1 in this row direction, not on column direction. Okay. So if you want it, it can be like this form as well, 1 and 0, and p is going to be like 0.9, 0.1, 0.5, 0.5. So there are two different ways to express the whole thing. I just want to make sure that you don't get confused with this two expressions, so that maybe at the initial time you might wondering, is this a stochastic matrix or not? Well, if you look at the column wise, it is not stochastic matrix, but if you look at row wise, it is. So you have to make sure in which form or which format that you are going to solve the problem, and based on that you can proceed. Again, in this problem we can go to the next state, x1, which is x naught times p. So you are getting results based on what we have in hand. So there are 90% chance that day 1 will also be sunny based on that, and whether day 2, the day after tomorrow, will be predicted in the same way. So we can predict the weather based on whatever data we have in hand. Isn't it interesting that we can predict the weather based on the current weather? Yes, that's all based on the data that we have in hand. Of course, we are dealing with data science, and how we can see this whole Markov process is helping us in doing this with the current data and probability measures that we have. So we can proceed with the next day also. So the next day changes in the steady state weather condition is varying. So based on that, it continues the whole process as we have done in the past. You can also do in the similar way. So the general rule also applied here as we have done in the past. The same process is being explained here, and with the different conditions and different process of probability measures. So here the vector represents the probability of sunny and rainy weather on all days, and is independent on initial weather conditions. So based on that, the whole process is happening. So I will skip this here. So this part is a simple explanation of how the regular transition matrix is happening with respect to the P naught and Pn entries. So initially we had the P values, probability values are given, and Q is the independent from initial conditions, and it must be unchanged when transformed by P. So we can also use the eigenvalues and eigenvectors to determine how this change in weather happens. So we have to understand that Q is unchanged by the P value. So that's where we are going to see how the P and Q are related to one another in this whole process, and the simple probability vector measures of the simultaneous equations when it reaches the steady state distribution is given here. So in conclusion, we come to know that 83.3% days are sunny. So here is another example, and I will let you to examine these examples of the stock market, and it's a simple example with all explanation given to us. And this is a hypothetical stock market in which we are talking about a bull market, a bear market, and a stagnant market, the three different states. So based on that three different states, the values are given, and you can eventually use these values. And in our state space, we are going to consider B as 1, bear as 2, and 3 as stagnant market conditions. So based on that values, you are going to also have this initial matrix. 0, 1, 0 represents that we have, this is considered to be the first one, second one, third one. So if you consider bear market, so you just have 1 as 0 here. 0, 1, 0 represents the bear market. So based on that, this distribution has been calculated, and finally you can also find this values. You can just proceed with the way we have seen in the previous examples, and you will arrive at the right conclusions. So this is the same state diagram based on the problem given to us. So you can refer the problem, and you will find they are matching with the diagram here. So that's what we have seen today. We understood what is a steady state probability, what is this stable state matrix. We talked about P naught, we talked about Pn, we talked about P power, we talked about this probability matrix when it reaches stability, right? So we talked about the stability of matrix, both forms, B bar and X bar, and how it can be attained. And we also talked about the power of the matrices. And we talked also about how we can predict various things, including the weather prediction, market prediction can be done. These are some of the real world examples of how Markov chain process can be used. So based on that, we can actually build a lot of data science applications. We can also see how the data analysis can be done with simple predictions based on the probability values that you have in hand. Yes, Markov chain process goes a long way, not just a simple probability measure, but it can help us in predicting things. And in the Markov chain process, if we have another way to look at this whole term, is called queuing system. So that's going to be your next discussion. A kind of Markov process is also a queuing process. So you are going to look at how this Markov process is going to be used in the queuing theory, and we are going to look at some of the applications, how the queuing theory can be used in data science in the upcoming lecture. I am looking forward to see you there in the next lecture. Until then, goodbye.